Segment 61B, Planet Formation and Exoplanets. There are by now really three branches of planetary systems studies. One of them consists of the investigations of how systems form, another of study of extrasolar planets, that is, planets around other stars, and the third is further studies of our own solar system. We'll be talking about the first two of these in this particular segment. The formation picture starts with the idea that a cloud of gas which has been stabilized by pressure and magnetic fields becomes unstable and begins to collapse. Because it has a small amount of net rotation as it collapses, in the way a figure skater pulling their arms in starts to spin faster, the cloud starts to spin more quickly. The central core condenses to form a star, but the remainder of the material that's moving the most quickly in the circular motion, forms a disk around this star. The material in this disk can eventually be coagulated to form planets by one of several means, and we're not exactly sure which way it gets done, either by gradually building up larger and larger particles, from tiny dust particles to rocks to boulders to big things that then become planets and then can sweep up the gas in the disk. And another idea is that there's some kind of an instability that develops in the gas in the disk that causes the gas and dust together to coagulate to form the planets fairly rapidly as a result of that instability. But whatever the reason, we now know that planetary systems are remarkably common. 20 years ago, we didn't know of any planetary systems other than our own. And that's been one of the major changes that's happened since I began teaching this class. The origin of planets is tied together to the origin of stars. So here's a picture of a part of the Orion Nebula, and you see embedded within it these little blobs, which in fact are actually, as we see in the blow-up on the right, little disks around stars that have just formed, and these disks are made up of gas and dust. So in particular, in say this one, you're seeing the shadow of the disk and some of the light from the star just poking out through it. These ones are particularly prominent because the radiation from the hot stars in this region are lighting up the outsides of the disks and showing them to us. But we have many other examples of young stellar systems where the disks are obscuring the central star if you look at them edge on, and then the radiation from the star kind of creeps out at the top and the bottom of the system, out the top and the bottom of the disk, and scatters towards us. And here's a few pictures of objects like that. Once these systems lose their gas and dust, most of their dust, you're left with a planetary system. And here's an actual photograph of one of these systems where what you're seeing is light scattered from the central star off the dust, showing you the dust in the disk of the system. We have such dust in our own solar system in what's called the zodiacal light. And the device here is blocking the very much brighter light from the central star so that you can see this faint scattered light coming from the disk. Here's another example where you see a ring of dust around the central star that's being shepherded around presumably by some planet that's in orbit around that star as well. Technology has developed to the point where we can now actually detect in some systems the real planets that are orbiting the star. So here's one of those systems, HR 8799, where 4 planets have been detected now in orbits of 20 to 100 AU around the central star. These are big planets. These are planets of Jupiter's size or larger, which makes them bright enough to see with that very bright star that's being blocked out by technology in this picture. So this is actually a direct observation of another planetary system. Most of the planets we've detected, however, we've detected by a more indirect technique. And one of them is by using the Doppler shift that the planet causes on the star, basically shaking the star back and forth as it orbits around, and they both orbit their common center of mass. By looking at these very small velocity differences for a planet the size of Jupiter orbiting a star the size of the Sun, the shaking is only about 11 meters a second. You can run that fast. But as you watch over time, you will see the effects of this on the velocity of the star, and you can sync those up until they show you one particular period indicating how long it takes the planet to go around the star. And if you can infer the mass of the star indirectly, you can then get the mass of the planet as well. This has been done for many systems. There are several hundred exoplanets that have been discovered this way, with masses from a small fraction of a Jupiter mass up to several Jupiter masses. And this is one of the recent catalogs of of such systems, showing the planets and their masses and their orbital sizes of these systems. Another technique involves using transit. So here's a picture of the transit of Venus from 1882, where Venus went across the surface of the Sun, and that transit caused a slight dimming of the Sun's atmosphere. This kind of experiment is very difficult to do on stars because you need a very stable system, and you need to avoid the confusion of the Earth's atmosphere, which varies the flux you would see in any case. And so a satellite called the Kepler satellite was sent up to do these kinds of observations of a huge number of stars at once. This satellite is able to detect tiny, tiny variations, a few parts in 10,000 of the brightness of the star as the planet passes in front of it. And this allows you then again to infer the orbit by planet passing successive times in front of the star. So here you see an example of actual measurements made with the Kepler satellite. Kepler has detected a large number of planet candidates, some of which have now been confirmed by the radial velocity technique, including a few that are only the size of the Earth or a tiny bit larger, but a huge number of planets around many different stars, showing that planets are extremely common in other systems.